In the last video, we were working on a separable differential equations problem, and rather than give us a separable differential equation to solve, we had this problem statement that described to us kind of a geometric situation, and in particular, we wanted to find all the curves that had this particular specification, that the derivative at points along those curves needed to be equal to 2 times the slope of a ray coming from the origin to a point along those curves. And what we found the solution to be was all of these parabolas and y is equal to 0, the line y is equal to 0. So in this video, I want to take the solution that we found in the last video and continue to try to work with it and come up with a new differential equation to describe another situation. And in particular, it's this one. I want you to now find the family of curves that are perpendicular to all of these parabolas. So again, you're going to want to construct a new differential equation that describes this situation here and solve it. So why don't you pause the video and work on that? All right, assuming that you've given it a go. Again, we're trying to make another separable differential equation and solve it. And in particular, this one is saying, okay, as we sample some points along these parabolas here, we want to find curves. All right, so let's make a tangent line here. So as we sample a point along this parabola, make a tangent line, we want to now find curves that have this specification. When they intersect these parabolas, at these points here, we could make tangent lines for these curves at that point of intersection. And we are wanting now these tangent lines, the tangent line that we constructed, the slope of the tangent line that we constructed for this parabola here, that slope to be perpendicular to the slope of the tangent line of the curve intersecting this parabola here. And just remember, if we were to just take this back a step or two, when we have two lines that intersect each other, their slopes are the opposite reciprocal of one another. And rather than talking about just the slopes of lines, we're now talking about the slopes of tangent lines. So we can now set up a differential equation off of that. We can say that the derivative, dy dx, the slope of the tangent line at that point, needs to be equal to the opposite reciprocal of the slope of the tangent line at a point along these parabolas, which we found that in the last video. We found that that is equal to 2 times y over x. So this is 2 times y over x. And this right here is our separable differential equation. So now that we have this separable differential equation, why don't you pause the video and try to find the solution to this? All right, assuming that you've given it a go. First thing, let's see here. We want to ultimately get both of our y's and dy's and x's and dx's on one side, but on different sides. But let's just first kind of deal with this denominator here. So I'm going to rewrite this as dy dx is equal to, and it's going to be negative x over 2y. Now let's multiply both sides by 2y, and we're going to get 2y times dy on this left-hand side, and then multiplying both sides by dx, we get negative x times dx on this right-hand side. And now all we need to do is integrate both sides, so we integrate both sides, and on this left-hand side, we get y squared, and on this right-hand side, we get negative x squared over 2 plus c. And if we were to add back over this x squared over 2, we would get this. We would get x squared over 2 plus y squared is equal to c. And this is what we get solving the separable differential equation. And what are these curves? What are these curves here? Well, these curves are actually ellipses. These are ellipses. And in particular, they are ellipses they're scaled versions of ellipses. So they're going to have ellipses. Maybe if we have an ellipse that looks like this, our semi minor axis is going to be in the y direction, semi minor axis, and that's going to have a length of the square root of c. And you could find that by just letting x be 0. And you would have y squared is equal to c, taking the square root of both sides. And again, we just want a length, so we get the square root of c. And then similarly, our semi-major axis is going to be in the x direction. And that is going to have a length of the square root of 2c. So it's going to be scaled versions of these ellipses here. And I graphed these beforehand, and you get a solution set that looks something like this. You get a solution set that looks something like this. And again, what is this solution saying? You can see that as we look at these ellipses intersecting these parabolas, we get some right angles here. We get some right angles. Wherever you want to go, we get some right angles. So you can see that these ellipses do fit this specification. Now, this is nice, and this is a cool solution. But the question is, all right, with differential equations here, when we find explicit solutions here, we need functions as our explicit solutions. Is this equation for an ellipse a function? Well, no, they're not. Ellipses are not functions. They don't pass the vertical line test. But a good thing, it looks like we can solve explicitly for y, so we can get some explicit solutions going here. So I'm going to jump back up to this line here, and we're going to solve for y. So we get the following. We get y is equal to plus or minus the square root of c minus x squared over 2. So these are our explicit solutions. And what does that mean? Well, both of these represent a top and bottom half of an ellipse. So our positive root here is going to be the top half of these ellipses, and the negative root here is the bottom half of these ellipses. And these are our explicit solutions. Okay, these are functions. And we said, remember, this equation for an ellipse is not a function. But these guys over here, these are functions. These are the top and bottom half of the ellipses. Now, these are solutions, but the question is, what about at the ends of these ellipses? What about at y is equal to 0? Are we defined there with a solution? Well, no, and you can see that clearly up in here when we talk about our differential equation here. That when y is equal to 0, the slope of our tangent line there is going to be vertical. It is going to be undefined. So y is equal to 0 is not included in our solution set. But we do have these top and bottom halves of the ellipses that fit this. And you can definitely see on this graph here that when we look at these ellipses intersecting these parabolas, we do have these right angles.